The next talk is going to be given by David Vincenzo. He's going to talk to us about
spin qubits.
Spin qubits.
So,
thank you.
It's a tremendous honor to come and talk to you on this occasion of our 100th anniversary. I was actually asked by the organizers to talk to you about spin qubits. I'm not sure that I would have chosen it myself. I work sporadically in spin qubits, and I would say it's an interesting case study in the subject that we've been talking about this morning, namely the quest to build the big quantum computer. I was very delighted to learn earlier in the week that I don't have to say that, we're on a quest to make a device with, say, 1 million qubits. And why do we do that? Well, now I can confidently say it so that we can solve completely the problem of the black hole interior dynamics. And I don't have to say that it's because we're going to mess up all the communication systems of the world. Now, I consider the spin qubits a beautiful subject in physics. So that I will defend completely. I will defend conditionally the idea that it's a real candidate for achieving a big quantum computer. I think, indeed, if I were a betting person, I would bet on one of the other possibilities at the moment. Or, I would have to take different odds to be persuaded to bet on spin qubits. However, it has a strong following, and it has people who work incredibly hard on it. And I think it's a beautiful case study of an interaction between theoretical ideas and experimental ideas, and not always with perfectly linear progress, with things that were blind alleys, with things that didn't quite work, the things that after reinterpretation worked really well. With attempts to invoke interesting physical principles that sometimes indeed match very well with how things can progress. I should get rid of Michael Faraday here, move to the next century. I'll try to take you through that journey. This will mostly be a sort of historical talk. However, I want to reserve the final minutes for a few views of what's happening now in 2025 and what are sort of the latest interesting developments. So let's see. So you see a bunch of pictures there, and I do indeed want to start with some history. I won't even tell you, you can read my outline a little bit, but I've just given you my own motivations, but we will take a bit of a path here. Okay, so I begin here with something that I don't believe any other speaker has done. We're commemorating the 100th birthday of modern quantum mechanics, but we've very little exposed the fact that those initial tremendous insights of the year 1924, 1925 were written in the German language. So, sorry, this is not very easily readable for all of you, some of you very easily. But I want to just highlight a few things about this. The smart people who fomented this revolution, one of whom was certainly Wolfgang Pauli, several of them were startlingly young. So I believe Pauli, at this time when he wrote these words, was maybe 24 years old. And Heisenberg was similarly young. So they were very young, very fresh, very brilliant. So Pauli had already written a book at this point, and his masterful interpretation of relativity theory was already written. It's you can get it as a fairly small book, but a very, very insightful book. But they were also very, very keen on understanding current developments in experiment. So Pauli was thinking extremely hard about spectra and how you could understand what was in spectra in those years. And there's a paper, but there's also this letter, which, as of a few weeks ago, was exactly 100 years old. Now the clock continues ticking, but he's writing to Landé, and at the end he mentions what his conclusion, and this was part of the revolution of that year, is that atomic spectra would not fit unless there was another quantum number. So there was what they would call a fourth quantum number, NLM, but now S. And he gives an initial sort of characterization of it, and the key words being that it's a classically not describable type of two-valuedness. So that's these words down here. So he recognized a new two-valued quantum number that had to be there. So this was indeed part of what sorted things out. It was the only way to make sense of experiments. So this was the first appearance of spin. It wasn't yet connected with the magnetic moment. That was a few years later. So here's, so I commemorate spins. So spin qubits can point right back to these words of Pauli. I wanted to just throw in one more thing of this sort. So as I said, the first 10 years or so after this were filled with incredible insights, and most of them, not all certainly, but most of them were written in the German language. And here's another example, which I think is not even so famous itself, but I feel should be, that Heisenberg describes in this paper to, I think, the Zeitschrift für Physik. He says that through the researches of Curio and Yolio, and it was only within previous weeks, actually, and the interpretation of Chadwick, I think Chadwick was also doing experiments, we must conclude, I'm being very free here, that the construction of the atomic nucleus must be, or a very important role is played by a new elementary particle, the neutron. And he recognizes immediately that it solves all sorts of paradoxes that were present at that moment, that the idea that there was a new elementary particle that, sorry for those of you in particle physics, of course not so elementary, but at this energy scale, very elementary, but with quantum numbers spin 1/2, so a new two-level system. But he also recognized in this paper that there was a new role for an abstract application of SU2 that not only was a neutron spin 1/2, but also that its relation to the proton was such that it constituted a new SU2 doublet, which then got to be called isospin. He did not use that phrase in this paper. So and this, a bit tangentially connects with the story that I'm to tell, because we care in spin qubits, we care both about nuclear magnetism and also about electronic magnetism. But also, what I don't show, but in the further section of this paper, he goes on and talks about the Hamiltonian of the nucleus, and in fact, that's the appearance of what we call the Heisenberg model, and the recognition that symmetry alone enforces a particular functional form of this spin-spin coupling, and I will invoke that quite explicitly in my telling of the story of the spin qubit. Okay, so that's where we are. I can use this machine, of course. I think if I point it in the right direction. Hello. Oh, no, I know what I'm doing wrong. I'm not using the advanced. Now, okay, jumping to modern times. So this I won't spend much time on, but of course, the subject of quantum mechanics and spin was never a quiet one throughout all of these years. My own personal entry, my own qubit, was the fact that I was working with experimentalists who were working on magnetic particles and quantum tunneling of the magnetic particles. So actually very far from what we would call a good qubit, but still, it was part of the quest in those years, like Peter Zoller described, that there was a huge prehistory that made it possible to jump in and say, we can make qubits. This was the one for me. But I'm coming indeed from condensed matter physics. So my examples come from, the construction of spin, or the appearance of spin in the condensed state. So now, of course, the Shor algorithm happened. For me, it was that the Deutsch-Jozsa algorithm had happened, and teleportation had happened, and quantum cryptography had long happened. And for me, that was enough to say, yes, this is going to come. And Shor's came, and I said, okay, yeah, of course. So even more so, we're going to have a very long quest to turn this into reality. Now, maybe I'll say that my very first efforts, I shouldn't have started with this slide, because this introduces the first sort of spin quantum computation, NMR quantum computing. I had written immediately, as soon as I was thinking about this, I wrote down some things which I have to, admit freely to be basically sort of science fiction. And I have to admit to that as a weakness, that I like to write down things that are essentially, I managed to get this published in the Physical Review, but it's basically science fiction. That, yes, you could have structures, mechanical structures in which you had spins, stuck on the ends, and you could move the structures around and have them in some kind of clockwork apparatus, and that was my quantum computer in 1995. Now, it hasn't really turned out that way. I can point to some elements of this that have inspired a few people, but the initial thing that it did inspire was the discussion that, well, okay, this idea is stupid, but there are ways, we have access to spins immediately, was the insight of several experimentalists of that time, and that gave birth to the NMR quantum computation, using indeed Heisenberg's insight that these atomic nuclei have spin quantum numbers that we perfectly well understand, and it happens in this molecule that there are a whole bunch of spin 1/2 nuclei. The fluorine 19, carbon 13 constitute a set of 7 spins, and maybe you had forgotten that the Shor algorithm has already been implemented 25 years ago. And yes, indeed, 15 is 3 times 5, as confirmed by these experiments. Now, there was a lot wrong with this approach. It was able to go a little bit further, but it was already clear that it was failing to satisfy some very basic criteria for, moving forward to actually be a quantum computer. You couldn't initialize the spins. There was no, way of scaling this. The couplings, you had very limited control over the couplings, although enough with, clever control techniques, which I would say have now been exceeded, but it was many years before experiments of the complexity of this factor 15 experiment were actually achieved. But still, it took a lot of work to use the limited control available in these instruments, but they were, real-life magnetic instruments to deliver pulses that would rotate specific spins on this backbone. Okay, but it was clear that, we needed to move on from this, and we sure needed to move on from my science fiction. Now, for me, I'm telling this somewhat personally, that a very seminal moment for me was a visit that I paid to Harvard, and I was in the office of Bob Westerfeld, I guess in 1995 or so, and his student, Carol Livermore, explained their new experiments to me, and that kind of clicked, it turned on a light for me, that they did experiments which I think are amazingly beautiful pieces of physics. It's sort of a realization of the Millikan oil droplet experiment, but in the solid state, in 2 quantum dots. These are 2 quantum dots formed in semiconductor layers, gallium arsenide, gallium aluminum arsenide. So 2 regions. You'll see somewhat more concrete pictures of this in a couple of slides. But they were able to, by controlling gate voltages, they could basically confirm that these dots held an integer number of electrons, and which could be changed one by one by the changing of gate voltages, and as documented by this so-called Coulomb blockade phenomenon. Now, actually, there were very comparable experiments at that time in Europe, but I wasn't. The name Van Wees is a very important one in that regard. But I learned it myself from these American experiments. And they had a quite inspiring diagram that said that as you changed the right voltages, that you could control the electron number, N1, N2, and you see they have 0, 0, 1, 0, 1, 1. Now, this actually was a fake, and I might have been slightly deceived myself that they only meant these to be offset numbers. And in fact, by the state of the art of that time, these numbers were more like 101, 102, 103. That is, they actually didn't have the technology to have individual single electrons in these dots. That required more innovations. I'll touch that a little bit in a moment. But that gave me license to have, well, a fiction, but not a super far in the future kind of fiction, you know, like more of these sort of dystopian science fictions that are set next year, but after the big war or something. I shouldn't say those sort of things. Okay, so the following year, with working with Daniel Loss, we tried to really lay out how this would, you know, with suitable, you know, modifications or changes of point of view, would lead to actually the first 2-qubit quantum computer. So we had pictures like this where the central pair of dots were theirs. And we took seriously that, yes, you could have one electron here and one electron there. That is to say, in the conduction band of these semiconductors. And fortunately, we weren't so far wrong in that speculation. That this became a reality rather soon. That is, this you know, actual charge numbers. And then we had all sorts of sort of things hanging off to say, well, you had to initialize, you had to measure, you had to do gates, you had to do all sorts of things. And then we went into pretty speculative vein. And I would say, you know, about half the things in this diagram have sort of come true and half have definitely not come true. Because we said, well, how do you measure this spin? Well, you use a so-called spin valve, SV, and you move it into this dot and you measure with an electrometer. And yeah, sort of, but in fact the phenomenon, so-called Pauli blockade phenomenon, was certainly the better way of achieving that. We would measure it by putting it into a metastable paramagnetic dot. Never happened, science fiction. We manipulated it with a nearby ferromagnetic dot. Well, also fiction-y, but I'll tell you the latest story on that. And you control the entanglement between these by changing gate voltage from high to low. That happened very soon, and that indeed was the you know, kind of good aspect of this story, that is indeed how things transcribed or transpired in the following years. Now, I'll say there was a sort of philosophy behind this that I would say it this way now anyway, that we try to stay as close as possible to an ideal of purely non-relativistic electrons, because that would very much clean up the dynamics, that would basically cut off, would establish a system with a very large symmetry group, and that would cut off many, many possible routes for errors, you know, coupling to environment. So spin and orbit are decoupled. So that was actually the point of making these dots rather irregularly shaped. It was implying, well, the orbitals would be deformed in some funny way. Didn't matter, because that would not by itself influence the spin dynamics at all. In non-relativistic quantum mechanics, the G factor is exactly 2, no matter what you do, no matter what the material environment is. And that's a very convenient thing as well. No sort of dephasing noise associated with fluctuations of the Zeeman G factor. Now, nevertheless, you can get entanglement, but it's a purely sort of statistical type of entanglement. The particle statistics determine that there's an exchange interaction, and it fully determines its functional form, which is this one. That is, the spin-spin coupling Hamiltonian is just isotropic, vector coupling between the two spin vectors, with some coupling constant. But unfortunately, the coupling constant does depend on environmental electric effects, because it depends on the height of the barrier. And that's been a bug, or it's been a problem with this, all the way through. So it's a very careful, management of charge noise, which would result in fluctuations of this coupling, has been necessary throughout this story. So you don't get easy, high fidelity coupling with this. So that's in my list of problems. But in the plus category, it's certainly that there's very very little, many decoherence channels are simply cut off. Electron-phonon coupling, goodbye. There's just not extremely good memory, basically. That there's very little that touches these spins if you're not in the active moment of doing gate operations. Nevertheless, gating required some definitely deviation from this philosophy, which I wasn't so proud of, that we ended up introducing many ad hoc things. Say, well, you probably don't. You want to do more. You want to do things that will make life more convenient, which is to add back magnetic effects, and that's partly what these pictures were invoking. And also, we had to think about, well, could you actually apply a magnetic field to this, an oscillating magnetic field to this dot, but not to that dot? And that's, then people have for years made micromagnets that would do such things. And it certainly had problems, but it was enough to get the ball rolling. Our notion of scalability was, we make a chain. We take the Livermore-Westerfeld experiment and we just make a longer line of them. And you'll see that is indeed what's been done over the years, and very little deviation from that. And it's not actually a very good idea for scalability, but it's what's been done. And it's part of this sort of slow progress that this field has suffered. You see in these diagrams, we couldn't resist putting in, well, you have the electrons live in one layer, and in some other layer there might be magnetization. In some other layer, the G factor might be high. So we're suggesting all sorts of things that I think the materials scientists sort of laughed at. They said, well, yeah, thank you, but such structures would be fraught with so many problems that we're just not going to go there. And indeed, I think the process of this influencing experiment was the experiment let it sort of wash over them and say, oh, yes. It sort of half sleep through these talks and then go back and say, well, what can we really do? And the first thing was indeed that it was quite difficult. Let me go through this. I'll come back to this vignette in a moment. It was actually quite difficult to measure if you had one electron here and one electron there. Why? Because the style of measurement was to flow a current through this pair of dots and see if it would go through. And that's why these dots get too small if they only have one electron. And so basically you can't get any current through. And so the big insight of those years, and I don't know who to credit for it, but it was, in a sense, it was shown by Philip Kim that the basic technology that's needed is an indirect measurement. And so to have currents flow elsewhere, not right through the dot, but flow through this quantum point contact. And then it was discovered, I credit Charlie Marcus, but I know that he was not the only one of those years who deployed this and showed that it really works, that yes, with that style of measurement, with this less direct style of measurement, you can observe the Coulomb blockade phenomenon and count it all the way down to one electron in each dot, or in fact, the fully empty condition of these two dots. So that all works. It's not like something funny goes on between 100 electrons and 1 or 0 electrons. It just works. And so the playground for this, our work, our Lawson Di Vincenzo work, was right here and became available, but after some years of effort. Now, they furthermore found it implausible that you really had as much control as we were hoping for. And so they made up a concept, or was actually from Jeremy Levy, that you could make a kind of qubit out of this pair, which was called the singlet triplet qubit. So a pair of states, but constituting the two magnetic quantum numbers that are possible with these two spins. I consider that a bit of a passing trend that had many sort of defects to using that as a qubit. It also led to kind of awkward control concepts, but it had its day. Mostly work is back, but with new tricks that I'll mention, back to thinking of the single spin as the qubit. Now, there was a sort of interlude that came from me not being really so satisfied with that I'd used a kind of symmetry principle, but only halfway. That this huge symmetry group available for non-relativistic electrons, would give you this Heisenberg coupling, Heisenberg exchange, but could I get a universal set of gates with that? And the kind of obvious answer is no, surely not, because in that setting, you can't just take one spin and flip it. So you can't get a NOT gate, let alone a controlled NOT gate. However, that's indeed from this point of view that one spin equals one qubit. And then with the representation theory of the relevant group, I credit the workers at Berkeley, Brigitte Whaley's work and of her collaborators, is that yes, in fact, it's possible, but you have to code. But this is not in the error correction sense of coding. It's coding by using symmetry sectors in clever ways in such a way to make the control problem tractable. And the trick was to encode qubits into multi-spin states, multi-electron states with specific quantum numbers of this group, but still to maintain the tensor power structure. And these were, well, somewhat new insights that you could take, for example, the singlet sector of a set of n spins, n being even, which does not have such a simple structure, but find a subspace of the singlet space that does have a tensor product structure. And but it would involve using clusters of 4 spins, 4 electrons, and the spin states of those would permit you to, take a conventional view of, yes, you have qubits. Each of these clusters of 4 constituted a qubit, and then you could, only with Heisenberg exchange, you could do the entire quantum computation. Now, there's a somewhat more efficient version of that involving only clusters of 3 spins, but with a slightly more complicated use of the irreducible representation sectors of this problem. I won't tell you that much more about it, except to say that, I mean, it's very simple once you say it concretely, that you say this particular state, which is a state of total angular momentum 1/2 and S sub z of plus 1/2, this state you could call the 0, and then there's another state with exactly those quantum numbers, but which is orthogonal to the first, which you call a 1, and so you build your quantum computation on that. And to me, that's the sort of high water mark of this philosophy of avoiding relativity completely. And then, indeed, it involved advice to the experimentalists: use very light materials, avoid spin-orbit coupling, choose materials where a G factor was very close to 2. And indeed, that has been a philosophy that's pursued mainly by one group in the world, but this is many scientists over many years at the HRL Malibu lab. I think they didn't burn down last week, but they have been, proceeding with this. It gets a little awkward of what sequences of Heisenberg exchanges you do to achieve the quantum control problem, and so I'd say it hasn't taken off. It's a little too complicated. But I think the really unfortunate thing is that the world is actually pretty relativistic, and indeed at the precision levels that we need. For example, in solids, G factors are not very close to 2. In some cases, yes, in silicon they're 2.01 or something like that. But in gallium arsenide, they're 0.44, and in other materials, they're plus 15, other materials we might like to use. So this non-relativistic approach is maybe not the best way, or it's a symmetry group that's broken too heavily for us to really use it in a precision way. Okay, now that didn't bother the people who were working in gallium arsenide. They proceeded along, and I don't have plots of it here, but as of 2005, there were plausible first entangling gates that were seen in these kind of structures. And work proceeded, but I would say slowly on these platforms. And I give credit to my colleague then at the Aachen University, who really continued to pursue this for a long time. But there was another problem that if you read the fine print of our original paper, we said, well, it's there, but it's no big deal. And we were totally wrong about that, because there's another problem about using non-relativistic electrons for your spin setting, which is that there are other spins in the world besides electronic spins, and they also mess things up. And and if you know anything about the chemistry or the nuclear nuclear magnetism of aluminum, gallium, and arsenic, they all, every single nucleus, every single isotope is high spin 3 halves, I think in all cases. And that's a terrible decohering environment for electrons. And now there are limits in which they're not so bad, but then it just becomes sort of environment management. And it's, it was done heroically in these, and progress was made in achieving higher fidelity gates, but it wasn't that easy. And definitely a large part of it is that this was just a bad choice of platform. This is about the worst semiconductor for these so-called hyperfine effects. Even though it was the most mature one for growing beautiful thin films and you could make dots and the electrons would be confined, but when you really got down to spin coherence, it was definitely not the best setting. So it was gradually, painfully realized that other semiconductors would be better. Now, these are not unfamiliar semiconductors, silicon, germanium, but it turns out they're awkward in other respects. The growth of really high quality heterostructure materials like this were not as well developed, it turns out, even though we have many examples of devices with those. We have, I don't know if we could count it, but we have, hundreds of billions of devices made out of these materials sitting in your pockets. So we would think we'd know everything about them, but no, we didn't. And we still don't to this day when it comes to their quantum behavior. Now, I should really proceed now to the, I get in the last few minutes to the present year. So I jump to this. Silicon germanium has improved, and indeed the progress is a bit speeding up, I would say. Fidelities have now finally reached a sort of competitive levels, and here's sort of an example of a structure that's built out of a silicon germanium heterostructure, and there's a boast that, well, we're on our way to 1 million qubits, and they could indeed put 1 million qubits into about this size, and I think that's all nonsense. I mean, in the US, you could make 1 million quantum dots, but you can't actually contact them all. So new ideas are certainly needed. There is a new development which will help that a little bit. So this is another one of these electronic structures, but it's made just to carry an electron from one place to another. And it's carry, in principle, a few microns. But the successful experiments, and now last year there are successful so-called shuttle experiments where this electron can be moved a good fraction of a micron and still maintain its spin coherence. So that's good news. It permits people to at least think of layout architectures where the spins are spread out enough so that you can at least think of coming and contacting them. And actually, the interesting development is that the attention has switched from electrons, adding electrons, to taking them away. Now, the holes in semiconductors, in the group 4 semiconductors, are an entirely different universe. The setting is one of the so-called Luttinger model. Luttinger has many fantastic models in physics, but the holes in semiconductors are a beautiful sort of vacuum. They have interesting symmetries. They're, of course, not spatially isotropic. They're multi-component because there's a lot of orbitals involved. They're very, very relativistic. So that's completely knocked out our original philosophy. This is an illustration of that. The G factor is in fact not close to 2 and is extremely anisotropic. The G factor for holes, if you go in this direction, is 20, and if you go in this direction, basically 0. That's what these plots are showing. And the principal axes of this large, small G factor are dependent on details of the materials. Now that doesn't sound so fantastic, but in fact, these experiments of this year have used that to realize one aspect of our original proposal. That is, they move a hole from one dot to another, and because of the change of principal axes, they get a big rotation. It's just like moving into a ferromagnet, and they've achieved high fidelity gates. After 25 years, or 30 years or something, it's possible to use that mechanism, one element of our science fiction, to do good gates. Now, that by itself is certainly not an architecture, and I'll just say that there are actually quite a lot of scientists from microelectronics who would love to put their chips, now I mean ordinary CMOS chips, right up against the qubits and then have some kind of interface and use that to solve the problem that you don't want to have millions of wires coming out of the refrigerator. You just want to have your Ethernet cables going in and all the rest done here. For the moment, I see this as very pie in the sky. I don't see this, it's great to announce and great to have some research programs. I think this is decades away from doing this. And I think the Google plan is just to have 1 million wires and to have a very, very big device. I mean, now I'm referring back to superconducting qubits, but I think the control and architecture problems of the two are rather similar. Okay, so my observations. Spin qubits, a case study of moderate success, and indeed still some flaming enthusiasm in some quarters and some companies and startup companies think this is the way to go, and I wish them well. I hope that they work. But in the meantime, we've seen resurgences of many beautiful areas of physics. The Luttinger model is one example, written down in the 1950s, very effective for understanding fundamental semiconductor physics in that era, relegated to a sort of textbook subject over the years and much less taught, but finally, revived and used again and with its beauty seen again. I think that I feel personally, just to say the last word, I think we will get to the 1 million qubit quantum computer, and I don't quite know how. So, thank you.
Thanks. Very basic question. So, this excessive decoherence or decoherence in this quantum dots. So, the structure is usually there's also these substrate phonons, right? Substrate phonons and electron phonon interactions in these engineered quantum dots. Mm-hmm. What are all the sources of this decoherence in these quantum dot systems? I mean, there are also these phonon effects, and then there is. So, can you say a little bit more about electron phonon coupling and the phonon effects in these quantum dots? And is that the reason for excessive decoherence?
Not always, no. As common in many qubit systems, there's sort of a long laundry list of things that can be the decoherence mechanism, and then sometimes one dominates over the other. And yes, electron phonon coupling has a role to play. It actually has generally not been so hard to circumvent. I mean, you kind of use the extended church Turing thesis. You say, oh, that qubit is terrible. And then you cannot conclude from that all qubits will be terrible. And of course, the duty of experimental science is to find the one that avoids the problems. So it turns out avoiding electron phonon coupling problems has not been that hard. But then on this laundry list, two-level systems, so, fluctuators in the environment, difficult, hard, requires the best growers, materials growers in the world to progress on that. Hyperfine effects, so as I mentioned, that's also sort of materials, and you say, oh, silicon, it's been solved. Not really, actually, because there's still, 100 parts per million of spins, and that's still enough to be trouble as well. What others? Cosmic rays, not. Okay, I give that one to Vijay. High energy particles, that hasn't been seen to be any big problem, unlike in the superconducting field. For that one, you maybe go a kilometer underground, but maybe that will not be a very easy solution. I don't know, standing here, I can't think of any more to really tell a nice story about. But phonons I'm not extremely worried about.
Okay, thanks.
One question there.
Yeah, I'm here.
Hi.
So, if you compare the superconducting and the semiconducting platforms and think about there's a lot of cryo-CMOS developments going on in the context of semiconducting. Once that happens, do you think the superconducting and semiconducting platforms will come at least roughly close to each other?
Well, I have to wait and see. I mean, as I say, you can go to an IEEE conference and hear many talks and groups working like crazy trying to make cryo-CMOS for various functionalities. And you hear their power budgeting, and you see there are many orders of magnitude from where they need to be to really be functioning successfully right near the quantum plane. And I don't know how they plan to solve those problems. So I think they've made progress by some orders of magnitude, but they have many orders of magnitude to go before they're relevant for that, for the control problem. It's maybe somewhat more urgent to solve it for the semiconductor case because, as I showed you, the new developments say that maybe you can make a device where the spins are separated by a micron or so. That's still a rather dense assembly of qubits. You know, it may mean that you have 1 million qubits in that space. Now, again, good luck delivering all million signals to that. You know, and then well, there are many, you know, concepts for how you do that, sort of global control so that one signal will do effective gates on many, many qubits at once, or I don't know what other things to invoke, but whereas the superconducting technique has the painful fact that 1 million qubits will take up maybe this much space, and everybody's been saying, oh, that can't be, why would you do such a thing? But it actually makes the control problem a lot easier. It's easy to bring in cables, 1 million cables into that much space. You just need a big room full of, your quantum computer will fill the room. Okay, but we've had such things in the past and they haven't been such bad computers.
Any other questions? Yeah.
Here. Yeah.
Yeah.
So you mentioned that the whole semiconductors are better and that's the future. So what about the nuclear spin? I mean, I remember Charlie Marcus's experiment, they were polarizing the nuclear spin.
Yep.
Then they had the decoherence time over which they could do things. Is it a similar protocol here or it's something else?
Well, again, these are holes in actually dominantly germanium layers. Germanium's isotope composition in our current universe is such that there is 93% of natural germanium is spin-free. There are few isotopes, and one of them is a bad high-spin isotope. So you invoke the idea that you isotope purify, you deplete the high-spin isotope, and then you don't have such big hyperfine effects. Holes also have the advantage that the wave function is very small at the nucleus. You know, it's basically a p wave function, so you don't have very much Fermi, essentially no Fermi hyperfine. You still have dipolar hyperfine. But the levels of the hyperfine constant are smaller, you know, luckily. So that, people think that may be enough. You know, you've heard already, we don't have to have perfect parts to do quantum computation, but we need darn good ones.
Thank you.
Now we have last question.
Hello, hi. This is it's here.
Where's here is here.
Here.
Okay, thank you. Yes.
It's a non-technical question. Your first slide was, I thought, Faraday lecturing about light. Was it to say that was this experiment about the two polarizations of light?
I haven't, okay, I know this is one of his lectures, Christmas lectures, 1856. I have not researched further which one it was, so I can't actually say for you which one it was. I do sometimes spend time on that picture because one thing is that a large number of women were in the audience, so it proves that we weren't always completely male-dominated.
Thank you.
So let's thank both the speakers for a wonderful presentations.